So hi everyone. This is intended to be an introduction to coding in R. This is a lot of why I personally consider R to be a lot better than Stata. I just find it more convenient and because of this kind of functionality that it has. So first, I'll start with the basics of writing functions. So first, in R, you'll notice that whenever you do anything, you're basically using an inbuilt function so far in this workshop. And the benefit of writing your own function is that you get to have a little more flexibility. You don't have to copy paste as much. It's easier to read. It's easier to modify. If you want to like do something to your data set and then or to multiple columns or something, and then you want to go back and you want to change how you did it, you don't have to like go to each spot in your code where you like repeated some series of actions. You can just go to your function and change it there and then rerun your whole script. So it just makes life a lot easier. I mean, it is definitely possible to like overthink using functions in terms of, you know, R already has a lot of functions that are there, but sometimes it can be very helpful.
I'm sorry, I missed something for a sec. Like, is this better than Stata because you can't write functions in Stata?
Well, okay, so you can write functions in Stata and things. Like it's a headache to do so.
Okay.
R is more, I think R is more intuitive for programming. And you can actually do, in my opinion, I think a lot more in R than Stata. It might also be I am more familiar with R than Stata. But there are definitely things in R that you can do that you cannot do in Stata, especially regarding kind of like saving objects that aren't as something other than a variable in your data frame, for instance. I'm not sure if you can do that yet in Stata. Stata only recently had an update that allowed you to have multiple data frames at once that are open. It's just overall, I find it much easier and more intuitive to use R. And I think that I think the other thing is R is like a full programming language. Stata is not. If you wanted to, I would advise against it. But my understanding is if you wanted to, you could do kind of things like making a website in R, but why would you do that when there's so many other better options? But you wouldn't be able to do something like that in Stata. It's not, that's maybe not the best example because that's definitely not the best use of R. But it is more, it does have more functionality. So when you're writing a function in R, it's really simple syntax. You have whatever you want to name your function, and then you have your function, you have whatever you want to call your function inputs, and then you have your code for whatever the function does to the inputs. Once you run, usually you'll write your function in a script and then you can like run that part and then it'll save in your like global environment part, the same place where your variables are stored. And then from there you can use it like you would use any function in R. So this would be like a very simple example. This is also a dumb example because, like I said, there's already a function that lets you very easily compute the power, right? You can just do like x to the y. There's no real reason to like write your own function to do that. And that's what I mean by like overusing functions. But sometimes it's nice to have a simple examples to see the like kind of syntax without getting caught up in details of like what's happening. So from here though, we can see there's a few different things that we can do that are important to think about when you're writing your functions. So first is default values. When you're using a pre-written function in R, like a packet, like one from tidyverse or something, say you're using, trying to think of one that I know most of the defaults for. Say you're using even just like even a base function like mean. You'll remember that there's an argument that you can add that's like na.rm, and you have to set it to be true to make sure that it's not including na values in the calculation of the mean. So that there, the default for that is like NARM equals false. Here, you can set your own defaults for your own functions. So here, this then becomes where like the default is to square whatever you're putting in. And this means that you don't have to put in multiple arguments in some cases. And it's really, this can be very useful when writing your own functions. And I'll get back to that when I talk about vectorization. This is also a little over the top for a function description, given how simple the function is, but it's always helpful to, especially if you're working with other people, to at the very least include a line saying like what the function does. If it's a very complicated function and it's not entirely clear what it returns, then it's useful to include what it returns. If your inputs are non-obvious, it's useful to include what kind of thing they should be or need to be. And in general, it's nice to have some sort of description of your function, and it's just generally a good practice to be able to, in order to help when like going back through code and things like that. And then the other kind of important thing to think about is the return statement. So in R, you don't actually need a return statement in your functions. So that's like this blue thing here. What R will automatically do is return whatever the last line within your function would return on your console, basically. So these two functions are equivalent. Yeah. So if you don't have a return statement, it will return the last evaluated expression. The other thing that's important is that a return statement stops the function at that point, and you can return at most one object. This doesn't mean that you can just return like one number. You can return entire lists or data frames or vectors or matrices, whatever you want to return, but it can only be one object. It can be a list of objects, which it counts as one object, but when you are returning it and then naming it, you're only going to get like one thing out. So these are a couple examples with like a slightly, not really complex, but slightly more complex function. These two both do the same thing with and without the return statement. You can see what it'll return is the last line if you ran this on your R console. And here, what you can see is if you try and do this, this computes the maximum of the two, and it will return this maximum. And this like line here will actually never be run, basically. R is just going to ignore that and stop at your return function. Whereas here, it's going to return, I don't know if this black is popping up, that's like blocking the code, but it basically, that's just M1 less than or equal to M2. That's going to return true or false about whether or not that expression is true. Anyway, so that's essential to think about when thinking about return statements. If you have a complicated function with like a lot of different things going on and you want to make sure that you're returning the right thing, then it can be very helpful to have, but it's not actually necessary. So the kind of like last thing for this part, for like that's just about functions. So your functions are going to appear in your global environment, as I said. If you want to remember where that is in R, that's over here, this environment here. If you run a function, if you run code that creates a function, that's what'll appear. There's a few different ways when kind of thinking about document organization that it's beneficial to put your functions. One is to just put all your functions at the top. That way it'll all be run first. You don't have to worry about it later in your document. If you want to like go back and edit a function later, they're easy to find. That just makes life a lot easier. And that in some cases, you might want to put your functions where they're first relevant. So if you're organizing your document, say you've got a section for simulation and you've got a section for data analysis and you've got a section for like a different kind of data analysis or something, and then you might want to have your functions within your section so that it's not like at the top you have a whole bunch of functions and you're trying to figure out where those functions become relevant later and whether you need to, whether they're necessary anymore, those kinds of things. It can be helpful sometimes to have them where they're first relevant. That does make it a little harder sometimes if you want to go back and edit, but obviously you can, R does, or at least RStudio, you can control find. So that makes it a little less of an issue. And then the last option is you can just put your functions in a separate file. And there's actually a command in R where this command here, where if you have like source and then you have a path to a file, that command is going to run whatever that file is. So if you, this way you can have a document where you've got all your functions going, so it can be a shorter document, and then you have your longer document where you're maybe doing whatever you need to do. And just at the top, if you source that first document, all of your functions are going to load in your global environment, and you don't need to worry anymore about like where your functions are coming from. Oh, so I guess any questions at this point?
I think we're good. Thanks.
So moving on to conditional statements. R has, so first there's a brief bit, there's this thing in R called the if-else command, and it will return a value based on a Boolean expression. It's particularly useful, for example, when combined with mutate. And this is just, if you imagine that you have like a data frame where you've got an age variable and maybe some kind of like employment status that, but a lot of times, for whatever reason, that employment status variable doesn't include an option for retired. I don't know why. You can, oh wait, oops, that was a mistake. This is actually not going to evaluate because retire age is not a Boolean. But anyway, the point here is that if you have this and then you have like the Boolean expression, what this will do is this will add a column based on this other column that's not just a Boolean. You can skip maybe the step of coming up with a Boolean column and then basing another column off that column. I mean, it's not entirely necessary, of course, but it's just a nice shortcut to have. And of course, you can nest it, as it's done in the second example. That is actually problematic because that's not a Boolean. But R also has like if-else statements of the kind that you would find in Python. So this allows for conditionals and functions. It's great for kind of like fancier randomizations. It's useful for warnings and breakpoints. And of course, as always, when you're doing if-else statements, you do need to be careful about edge cases. I mean, that's kind of, I guess, a general rule if you're writing a function, but as long as you're if you're the person using the function and you make it clear, then.
Sorry, could you explain what an edge case is real quick?
Yeah, so an edge case is like if you have let's say that you have a function that does things to a vector, right? Or a data frame. Let's say you have a function that does things to a data frame. What happens if you put in a data frame with no rows, right? And usually that'll just give you an error. And there's not a lot of occasions where you'd want to put a data frame with no rows into something and then have something be done to it. But that can, in some cases, cause a break in your function. Or if you have something where maybe, I mean, what an edge case is can vary depending on what you're actually considering. But if you have, say, a function that you're trying to apply to a vector of numbers, maybe, if you maybe think, oh, these are people's ages, there's nobody who should be 0 or negative, those are both edge cases if those actually might appear for whatever reason, if there's like an error in the data or something. There's also another, I think a maybe more common issue would be something like an empty string, where you have like a string where you don't have any characters in it, and then if you try and like make a substring out of that string, you will get an error of some kind, or you might just not get what you want. So that's what I mean when I say be careful about edge cases. It's if you're like doing this for like your p sets or something, and you're just like writing a function that makes your p sets easier, you probably don't need to worry so much about that. But if you're going to get like very involved and maybe in using R for simulation, which there are like R may not be entirely the best tool for simulation. I think most economists who are simulating things are using like MATLAB or Python. But in those cases, you'll still need to worry about edge cases when, especially like when kind of doing some kind of long, a long script that you may expect to be using on a lot of different things.
Thank you.
Yeah. So these are what ifs. So in R, you don't need an else part for your if statement. The most basic thing is just if is where you just have this statement that begins with if. You have your test expression, which should evaluate to a Boolean, and then you have whatever code you want to run. So if you ran this code, you would get less than 10. If you ran this code, you would not get less than 10 appearing in your console. Yeah, and then you can always add an else part to it. So in this case, running the same thing with simply since R evaluates modulo first, with your parentheses, you still get the less than 10, but this time instead of getting nothing, you get the actual value of X. And then if you have maybe 3 conditions, you have like a first condition and then a second condition, and then a third condition, you can have an else if in the middle. And so it literally just does the same thing. It takes this other test expression in, and then your else becomes, assuming that both of these are false, this is what will be run. Yeah, so the difference between the if-else statements and the if-else function is that the if-else function is vectorized, which I'll get into a little bit more about what that means later. It's faster, and but it does mean that it's like it is basically purely intended to be used for vectors, and vector in like the broad sense, not necessarily like vector as in a point in the like a point in RD, but anyway, so then the if-else statement, it has a little more flexibility. I think it's a little more readable sometimes, but it's like that's probably a bit like personal preference there. I find the if-else statement to be more useful when writing functions, and the if-else function to be more useful when like adding columns to data frames, which is why that was the example I gave. So if you want to use it in a function, you just toss it into the function. Honestly, you can put whatever you want into a function, and that includes if-else statements. And then what happens here is that here return statement placement matters. So for instance, if you had like this function, you can add this if-else statement, and that'll return it in this way. And what it does is when you have this return M1 here, if M1 is greater than M2, it will actually break the function at that point. It'll return M1 and it'll ignore everything after. You can actually note that here, like adding the if statement into the function produces worse code. Like there's no reason to do that whatsoever. It makes it more complicated. But this is just kind of intended as like a just example to like just see what it looks like. So note that you don't need, I guess, the return around this M2 here. You also technically don't even need the else part. You could just have an M2 at the end, and that would also produce the same thing. And something that can be useful is using if statements as a warning. So here it creates this like warning that will pop up if you use this function and X or Y is not a number. If you didn't create this error message with the print, with like the if statement and the print, you will get this error anyway. Actually, even with the error message that you create, you'll get this error about it being a non-numeric argument to a binary operator, but it wouldn't tell you which one it is. So that can be a benefit here, kind of, if you have a function maybe with a lot of inputs, and you want to make sure that your function is not going to break randomly and give some weird error that may or may not be easily understandable. Here the error is because it's a very simple function. But in other cases, it might not be. If you want to just check to make sure that everything that's going in the function is the correct type of object, you can have error messages like this that appear and just put those in your function so that if you've got a function that you're writing and then you expect to be using it for a long time, including much later when you maybe haven't much later than when you've written it, so maybe you don't remember what all the inputs are anymore, this kind of thing will let you know that that what you put in is like problematic in the particular way that's easy to fix. And then the other thing that functions are really useful for, at least in my view, is randomization. So for instance, so you can very easily use it to take some kind of like random number and create your own new distribution, or if you want to like create a random function for whatever reason, which again is very helpful for simulation. Like if statements can be very useful in kind of creating your own distributions from like R uniform, from like the uniform distribution. If you recall from, I think that was the very first R session, what RUnif does is it takes, it draws from the standard uniform distribution, and it has a lot of default values. You can change those defaults, so it's no longer the like 0, 1 uniform distribution. And it gives you a random number in that distribution, or it gives you n random numbers in that distribution. Here, I just put one in because I only need one to like do a 50-50 randomization. But you can get like 3 random numbers drawn from the uniform distribution or however many you want. Okay, any questions here? Okay. So moving on to loops. This is going to be very familiar if you've like coded, I think, in other languages. So a for loop repeats over a vector. Your structure is, sorry, for something in a sequence, some code that gets run and you run it throughout that sequence. And so this is just an example. You can note that this doesn't need to be like a 1 to 15 type sequence. With I being a number, it can be whatever you want. And it'll just loop through, taking each value in that sequence. There's actually a reason why for loops are not as common in R that I'll be getting to when we come to vectorization. And then we have while loops, and while loops will repeat until a condition is satisfied. Something that's really important for while loops is that your test expression must be something that will be reached. Otherwise, you'll have a problem. I mean, you will have to basically break it, and depending on, I guess probably how much memory your R Studio's or your system is using, it might be difficult and frustrating. So an example of a while loop would be something like this. So here, this is essentially finding when the first what like the first power of 2 is that is greater than 300. And you can see it's really important that whatever's in your expression is being affected while in your while loop. And it's like that, for instance, that this I is being incremented and that this N is being changed, because otherwise it would just like run forever, or well, until you broke it. But yeah, essentially forever without outside interference. But there is a better way for a lot of the things that you might want to repeat doing in R, and it's vectorization. So R structures things in lists, and this is why it's really great for data. But even a data frame in R is basically a list of vectors, and they're just named vectors with whatever your column names are. So everything in R is structured in lists. Vectors are smaller lists, and then you have your lists of vectors. And so something that's really great about R in terms of speed is vectorization. which is basically where whatever you want to do, you change in a way that it can be run. If you want to repeat something, you change in a way that it can be run over a vector, and then you can run it simultaneously over every element in the vector instead of going one by one. So if you have a for loop, what you're doing is you're literally going through the loop each time. When you're vectorizing, you're not doing that. I'm not entirely sure like exactly how it works, but it's a lot faster. Yeah, so why vectorize? It's faster. In some cases, it can be a lot more convenient. And it's a better usage of R. It's the whole reason to, it's like a reason to, it's one of the things that would be like, oh, if you have something that needs a lot of that could be affected a lot by vectorization, then it's good to use R relative to other languages or systems. So there's a few common vectorized functions that I'll go over. There's some others that you can find, and you might find in Stack Overflow at various times. So first is if-else, which was already discussed. So that's like, basically what it does is it checks a whole vector based on a conditional statement very quickly. Yeah. Okay. So then there's lapply, sapply. There's also a few more, like, I think there's like bapply and another one. Anyway, and they apply a function to some structure within R very quickly. I believe sapply must be used on a vector. Lapply is the most general. So if you're not sure what to do, you can try it with lapply and then try it again with like sapply or dapply and see what comes out. That's what I usually end up doing because I can never remember what precisely each one is. And the basic syntax is that you'll have your first argument, which is the thing to apply the function to, your second argument, which should be the function that you're applying, and then whatever other arguments. These functions do have other arguments themselves, and then if you've got your second function, which is your function to apply, all other function arguments must have defaults so that it knows which function argument to apply the things in your vector to. And then you can change those defaults basically as other arguments directly in your lapply or sapply.
Sorry, what is the, I don't know if you said this, I might have missed it, but what's the difference between like lapply and sapply? And like, why would you choose one or the other?
Yeah, so lapply will basically take in almost anything and will return a list. Sapply, I think, only takes in vectors and returns vectors. It might take in more than just vectors, but I know it generally returns vectors. Lapply, actually, no, wait, let me think through. I don't want to say like completely incorrectly. It might be better to just like check the documentation.
Okay, yeah, that's fine.
But sapply, I think actually no, sapply returns in the simplest form of whatever you put in could come out as. Because I know that if you put in a vector to sapply, it'll return a vector usually, assuming that whatever function you're doing is vector to vector. Or like item to item, like not item to list or something.
Right, okay, thank you.
And then the last one is replicate, which allows you to repeat a random function. So this is particularly useful for like simulations. It allows you to just like repeat something a whole bunch of times. And so some examples for sapply and lapply. So if you have some sort of function that like gets like the square root of something, and then you want to apply it on the first 15 numbers just to see what they are. I don't entirely know why I'd want to do this, but simple examples. If you use lapply with get root, you'll get a list with 15 elements. And so what that means is it can be in order to use it in certain ways, you might have to unlist it. There are some reasons where you'll want to list back. There are functions that can be very easily applied to lists in R. Obviously, the people creating packages for R who are typically very familiar with R, they know how to, they will, so there will be functions that are easier to use in, that are easier to apply to lists in some cases. And then if you use sapply, the simplest thing you can get back from a list of 15 elements that you want to apply the square root to is a vector, so you get a vector of length 15. replicate is very useful, and it doesn't just produce vectors. So here, for instance, this one would produce a vector of length 4, which is like 4 random draws from uniform distributions. This would be kind of pointless to do because you could already do R unif with 4 instead of 1 and get a vector of length 4 with 4 random draws from the uniform distribution. But you can also get like a matrix from this. So you can get like, so for instance, if you did instead R unif 3, you'll get a 3x4 matrix. And importantly, this is not equivalent to the function rep, which it's easy to get confused by, but rep, I believe, is for repeat. And what it does is it will produce the same thing multiple times, right? So and it has a different syntax. So if you did this for repeat, you'd get this like this one random draw from the uniform distribution, and it'll repeat it 4 times. And if you did this with 3, it would actually still produce a vector, and it would produce like your first number, your second number, your third number, first, second number, second number, third number. Like it'll repeat that draw 4 times within one vector, not within a matrix. So like I was saying, loops versus vectorization. Vectorization is a lot faster in R. If you can vectorize, you should. But sometimes it can be easier to think of something in a loop. I think there's a lot of cases where, just kind of if you're intuitively thinking about how you want something to be done, you think about it in kind of the more of a looped way. There are cases where I think there are some cases where it is easier to use a loop. So like if you wanted to do like the Fibonacci sequence, for instance, which I was thinking of doing as a quick example after this, I find that at least for me, it's definitely easier to figure out how to do that via a loop than via vectorization. I'm not actually sure that you could do it via vectorization, because it's recursive. So in that case, the loop becomes actually important because you're wanting to not apply the same thing, apply something to a whole bunch of different numbers. You're wanting to see something happen to the output over and over again. Okay, so moving to examples in R. Let's see, not R. So moving.
I'm so sorry. I actually have to go right now, but
no
thank
worries.
you so much. Yeah, really appreciate it. I'll definitely catch the rest of the recording. So thank you.
No problem. So yeah, so moving to examples. So we have, for instance, the Fibonacci numbers, which is what I just mentioned. This is something that it's like really convenient to do in a for loop. So you want to like maybe compute, if you wanted to create a function to compute the nth Fibonacci. I cannot spell. You might want to have you could very easily do this via a for loop. You would have for, and then you'd I is kind of standard simply because it's like could be like stand for like index, so it's I think fairly standard across a lot of languages or coding to use I. So for I and in 1 through n, you definitely want this to be a vector. You would want to do you need to initialize. You'd have f. You wanted f to be let's say f. Wait. So you'd want to have, this is going to be like initial, second, first, and then out, or O for out. So you want f out to become f to f minus 1 and f minus 2, and then you'd want to make sure that you've got f1, like f back 1 to be the same, and f1 to be to go to, right, you want this in the other order. Should have just written this down previously. And then you would want to return f out. Here it's helpful, you want to like return it because otherwise your last thing is going to be this f0. See if this will work. So you can see it's appearing in your functions here, and you can do Fibonacci 3. Oops, object not interpretable as a factor. Oh, that's because I did a capital C here. Now, if you do Fibonacci 3, you'll get 5, which is not the third Fibonacci number because it's the third number, I guess, after 1. So you'd probably want to make this more intuitive, so you actually are getting the nth Fibonacci number. You'd probably want it to be n minus 2. So that way, yeah. So then you're getting the third Fibonacci number as 2. This, you'll notice, is actually going to cause a problem if you want to get the first or second Fibonacci number, although I don't know why you would, because then you're not going to get a proper function here. So that would be an example of an edge case that you would need to consider. Now, something that maybe you want to generalize this, maybe you actually want to be able to start with any 2 values. So you can do v1, maybe we can add v1 and the default is 1, and v2 and the default is 1. And you can change this to v1 and v2. And that's a very quick way of just kind of generalizing a function or something that you come up with for like something specific into something a little bit more general, right? So then you could compute the Fibonacci number, like the, why can I not spell? Fibonacci, like maybe the 6th Fibonacci number if you're starting from 1, 1, or you can compute, say, the 5th Fibonacci number if you're starting from 3 and 5, which you can obviously is just a lot higher because you're starting with higher numbers. If you're using Fibonacci numbers, if you're familiar with them, you'll be aware that you can actually compute a Fibonacci number directly, in which case this whole for loop becomes unnecessary, and you can just compute it using this formula. And I would recommend that, like as practice, you can maybe like make a function. But note, of course, that that's just for the original Fibonacci sequence. That wouldn't this formula wouldn't work for other sequences. That starting with like, I don't know, if you wanted to start with like -3 and 24 or something like that, this would not work for that. Of course, for like any Fibonacci-esque sequence, there are other like sequences obviously where you will need to include a loop. So for instance, and that's why I said I have like Fibonacci-esque sequence as a spot here. For instance, you could create, I don't know why you'd want to, but you'd have like, let's say sequence. Maybe you'd have a sequence where half the time it adds the previous 2 numbers, and half the time it adds the previous 3 numbers. I don't know why you'd want that. And here you can see I'm starting off already with the V1, V2, V3. So you can do something very similar. On the one hand, you shouldn't copy paste code too much. On the other hand, it will make your life easier to do so. And here is where you can do and here is where you can use randomization, for instance, and with an if-else statement. If, obviously there's no particular reason that it needs to be 50-50, but in this case, and you don't really need an else. You do need an else if you don't want it to also be run. So if I didn't include this else statement here, it would run even if this statement is true, which in some cases you don't mind. So for example, back here in these slides, when we had with something like this, where you have a return statement at the end of your if part, you don't need this else because this is only going to run if that hadn't run anyway because of the return. But because here there's not an end that's going to like break it, you do want to make sure that you've got your else statement that's actually there. So now you want to rename F. Oh wait, this I counted differently. So here F2 is the most updated one, so you want to rename F0 as F1 and rename F1 as F2 and rename F2 as F out. And then return F out. So this would be like a randomized kind of Fibonacci sequence of it. And moving on. So another example would be to like do, and this is one where you could do it in a loop, which is maybe the first way you'd think of it, but it's actually better to vectorize. And this is the random harmonic sum. So if you know what the harmonic sum is, it's the sum of it's the sum of like 1 over, it's like the sum of 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, et cetera, and it does not converge. But there's a randomized version of it where sometimes it's multiplied by -1 and sometimes the number is multiplied by +1. So if you wanted to find, if you wanted to create a random harmonic sum to see maybe whether it converges in distribution to something in particular, or whether there's no way, or whether this like, or whether the distribution ultimately has a mean or something like that, you could create a function to find the nth number of the random harmonic sum. And so what you'd want to do here is you'd want to create, you could very easily create a vector that say of like sequence, you'd want it to be sequence let me think for a moment. Yeah, so you'd want to start with a sequence from 1 to n, and then you want to turn that into the sequence of 1 over that. So for instance, you could already vectorize here. You could s-apply. It actually is easier to do. Think of one number at a time. So you'd want to harmonic 1 val. So here you would maybe have a function that you can take for a net value x, and for that value x, what it does is it returns. So you'd want to select either 1, select from 1 or -1. You want to select one value from that. Let me just double check. Okay, whatever. It's just easier than to, you can use again this. And instead we'll have y is x, or we'll have y is negative x, or x times -1, just to make it a little more clear. And then we'll want to return 1 over y. And then here, you can see that that's something you can apply to one value. And then you'd want here, to create your vector from 1 to n, and you can use sapply and get from to sum. You can use this randharm1val function. And what this will do is it'll return that function applied to each of these. And then you'd want to return some vec, because you ultimately want to get that random sum, right? So then you can run randharm. Let's see what happens with 3. You can see that clearly the 1 was negative, the 1/2 was also negative, and the 1/3 was positive. But if you run it again, you get a different value. There, all 3 were negative. And you can run it again and again, and obviously you can run it to things like 1,000. And you can see that actually doesn't take very much time. And the reason that takes so little time is because you're vectorizing. I think I'm going to skip this one and leave this as an exercise. Have fun. I'm just going to add to the exercises here. So this is an exercise that would be probably be good to use a while loop on, and it would be to find, let's see, write a function that finds the minimum power you must take a number to be larger than some threshold. And here, and I will remove that from the example, or maybe I'll put in it, or maybe I'll fill that example in later, and it won't be an exercise. And then I think I'm just running out of time, so I'm going to fill this in this evening fill in the example more thoroughly this evening to go back and show you. But this extended example is you can do like really full-on simulation type things here to simulate a lot of randomness. So the idea is that, for instance, you could something that's important when thinking through these kinds of things is to simulate in steps, right? So if we want to simulate like a monkey writing on a typewriter, and the reason I was thinking of doing this was because it is not something that you'll probably be asked to do for your classes or for your research assignments ever. You want to start by thinking of, okay, how can I create a random string, right? And then you can go from there. How can I create m random strings? How can I create m random strings with random lengths of words? And so on and so forth. And then you'll want to think from there, okay, let's make this a little more complicated. Let's add in some regularity to this, right? Like maybe we want to emulate a monkey writing on a typewriter, in which case you would have different letters according to the QWERTY keyboard. Like you have the letters in the middle, maybe have a higher chance of getting hit than letters on the edges. Maybe instead you want this to be kind of like a pseudo AI kind of randomization, in which case there are rules that must be followed in English. You can't have a one-letter word aside from A or I. Q is followed by U. Like all of those little things, vowels need to be placed every so often, or else like doesn't make sense. Things like that you can add as like additional layers. But if you're ever coming across something where you're having trouble, it's really beneficial to just think, okay, what is the simplest next step thing that needs to get done, and then go from there. And with that, it is just about 7, and I will fill this in and commit it. I'll commit what I've already done, but so now if you go to your branch on GitHub and you pull from the main fork again, you will once again get all the materials for workshop 6. Later this evening, I will write up some functions, or maybe I'll just write hints on how to do the functions for the kind of extended example. And I will push that, and then I will send the email with the details on how to access this week's workshop materials. And the video, I guess. So you won't be seeing this video until I've sent out that email. And with that, good night.